Okay, so hello and welcome to this English talk about Racket, a modern scheme implementation. This is not going to be, let's say, something that you should expect to give you some knowledge about how to program in Racket. No, my plan was to show you what you can do in a modern scheme or Lisp implementation and what problems you might encounter using it. And actually the reason I wrote this talk, and I'm giving this talk today, for so many people, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. Wow, that's interesting. Although we are talking about language conceived in 1965, there are 10 people here, and most of you aren't 70 years old. That's great. The reason is, for past like 5 or 6 years, I've been developing mostly in Racket exclusively, and for the last year we've been developing some cryptographic solution, and we've been using Racket like exclusively for everything related to the development of both software and hardware. So let's start and see what you can do in a modern scheme implementation. Racket, as I mentioned, is a modern scheme dialect. We used it for embedded computer vision, for manufacturing quality assurance. That means some recognition what's on certain images. We'll get on that pretty quickly. We use it for desktop applications development, and very interesting thing is that USB hot plug. This is LinuxDays, so, and honestly I'm using Linux exclusively since 1999, so it would be fine if this worked just in Linux. But the cool thing here is this works cross-platform, including, for example, that USB hot plug. So we develop once on Linux, and when customers need it, they can run it on Windows or whatever, macOS, you name it. It's really, really cool. And last thing, big numbers crunching. It sounds boring, but I'll try to make it really fun, which is something I often say to students. And, you know, fun can be everything. We just need to define what we mean by the word fun. And that's going to be fun. I mean real fun. So if you stay for the next 50 minutes, I hope you'll enjoy that. So let's start with some introduction, what a Racket is. It's a dialect of scheme, which is a dialect of Lisp. What does it mean? Yes, lots of stupid, irritating parentheses. That's what it is still after 60 years. It's got a web page. You can download it there for most platforms. It's got a nice logo. By the way, that logo, that's the lambda symbol from lambda calculus. We'll get to that later on. The motto of the language is solve problems, make languages. And I think this is the main distinction between scheme or Lisp-based programming and traditional programming in imperative languages like whatever, Python, Pascal, Visual Basic, you name it. The reason is it's kind of a meta language, and you can define your own languages, including specific syntactic forms, which sort of spares a lot of time sometimes. There are pretty useful languages included if you download it, like the Racket itself. That's the modern scheme implementation. There's a Scribble language, which you can use for writing documentation, or even use it for annotating the code with some documentation, or typed Racket. You might not know the distinction between dynamically typed and statically typed languages. Truth is, in most of modern languages we see students using, like Python, JavaScript, and such, there is no static type system. You just assign some value to a variable, and if it's a number, well, it's a number. If it's an object, well, it's an object, and you can distinguish what is what. In typed languages, you say what the type is going to be before you use the variable, which is kind of work you have to do in advance, but it pays off usually with better performance. So we'll get on that later on as well. There are, of course, some less useful languages. Algol 60. Please raise your hands who knows how to write programs in Algol. Oh yeah, that's it. No one. Lazy Racket. That means of course, I always tell students, be lazy. This is not the case. This means lazy evaluation. That means you write the code, and the expressions get evaluated once the result is needed. So you can write, for example, infinite sequence. And until you try to get all the numbers in that sequence, it's fine. If you want to get just the first 1,000 of numbers, it will evaluate those 1,000 results for you. And a revised report on the language scheme number 6, which is the latest standard on scheme language. I know there's R7 RS, but that's a step in completely different direction, so there aren't many implementations. And of course, how to design programs languages. What is it? How to design programs? Actually, Racket started as a fork of Scheme I think at the University of Utah in United States of America. And the group developing this programming language was called Programming Language Theory Group. So it started under the name Scheme-PLT, but you know, that's not very catchy name. What are you programming in? Hey, oh man, I'm using Scheme-PLT. That's not good. So the name Racket was chosen because, you know, it rhymes with bracket, and there are lots of brackets. How to Design Programs is a book written by Professor Matthias Feleisen and Matthew Flett and a few others, which teaches beginning students with no prior programming experience how to design programs. It uses the Scheme-PLT, now Racket, as the language of choice, but it uses simplified versions for beginning student, some beginning student with some functions added to it, intermediate student with Lambda, we'll get to Lambda later, and advanced student. And then, of course, the course is to help students learn the actual Racket, which means full Scheme-PLT. So, how does it look like? Typical example, hello Racket. First line, we state the language we want to use. So we use #lang, space, and the name of the language, in this case, Racket. Then we use the function display line to display a string. So we see two components here, a function call and a string constant. This looks probably very strange to you. It's called prefix notation, and it means always first thing to do is the function or an operand, and then there are arguments. We'll get to that later as well. If you want to run the program, we just say in the terminal Racket hello.rkt, and it prints hello Racket. I think you would expect this. So the thing is, everything is SEXP or S expression in Racket. That means symbolic expression. What is symbolic expression? That's basically just a list delimited by parentheses or brackets, or in this case curly brackets. Actually, it doesn't matter, because in Racket, contrary to original scheme, all the brackets are equal. You just need to pair them. So you can use different brackets if you want to make the code look different in some parts, like if you want to, for example, state what are the default values of some arguments. You can put it in brackets. Personally, I prefer to use parentheses, that means round brackets, everywhere, because I'm lazy. The good thing is, although it looks slightly alien at first look, the source code maps directly to abstract syntax tree of the program. It's really easy to write a tokenizer. Maybe some of you have written some simple interpret for some Lisp variant, because it's really easy to write a tokenizer. It's really easy to load it into some memory, in-memory structure, which represents the abstract syntax tree, and just interpret the program. So that's the reason for this, and it really simplifies a lot of things. First, let's have a look at some basic expressions. If we want to define some named value, we bind the value to some name, that's how we call it. We use a define form. Define how it's going to be called and some value. In this case, it's going to be called something, and it's going to be a value 1, 2, 3. That's 123, the number. If we want to create anonymous function, because in most languages that arise from Lisp, functions are normal data type, like a number or a string. So there must be a way to create a function value, and it is. It's the lambda. Lambda, then we give an argument list, which might be empty, and then we give some expressions what it should do. You might notice there are two forms actually. One spells lambda, L-A-M-B-D-A, and one there's just the Greek letter lambda. Of course, you can use any Unicode symbol, which is denoted as some alphanumeric character. Forget about emoji in function names. That's not supported. Thank God. We can define and call a function. It's rather simple. If we define a function, once again, we are just binding a value to a name. So we create an anonymous function and bind it to a name. That's all. And if we want to call it, as I mentioned at the very first example, we just write a list where the first value or first term is the name of the function, and then there are the arguments, and that's all. Of course, there's a shorthand for defining a named function, which might resemble other languages, and that's you just say define. Oh, and there's missing name of the function that should be in the argument specification. So you say define, bracket, name, arguments, and ending bracket, and then what it should do. Now, if you are new to this, and this really might look alien, there's a nice tool that will help you. It's called DrR Racket. And that's basically something like an integrated development environment which can do code introspection like in real time. So as you are typing, you immediately see where are your definitions used, where you import them from, and it's really pretty cool, and it helps you speed things up if you are new to Racket. Also, it contains things like steppers for syntactic macros. So if you are writing something complex and you are not sure what it does, you can go step by step in any stage, in compilation stage, in running stage. It doesn't matter. It really allows you to study how the program works. That's actually a very useful thing I'm using pretty often. So this is how it looks from the programmer's perspective. Now, behind the scenes, there are several backends you can use. First, the Racket programs are compiled to some byte compiled intermediate language. And there's a virtual machine for this, which uses some conservative garbage collector. That's the old way to do things. Now, there are actually two better options. First, once again, the Racket's own virtual machine, but now using the moving memory manager, which keeps track of all the allocations and does sort of proper garbage collection, even in case you are doing some crazy stuff like I tend to do. And do you know what a SHE scheme is? No. Yes? No. It's a scheme variant sponsored by Cisco. And actually, it's really good when it comes to performance. It's really fast. It's really effective implementation. What the hell has happened? Oh, wrong button, sorry. And now you can use SHE scheme as a backend for Racket programs. So they can be even faster, but we'll learn later on that they can be damn fast. Of course, you can get SHE scheme at scheme.com or on github.io, and you can download the Racket version, which uses SHE scheme at racket-lang.org. Now, as I mentioned, we are using it for cross-platform development. So what operating systems does it support? Of course, GNU Linux, Mac OS X, yes, NetBSD, I know you were waiting for this one, and Windows, although we try to keep away from that. And anything else you can try it on, it will probably work. As long as you've got a C compiler, you can probably compile the whole Racket there and use it to some extent. So a quick introduction to some forms we'll be using. structures. You probably know structures from other languages. So you can create a named structured type, which has some fields, and you can tell Racket if it's going to be mutable. By default, nothing is mutable in Racket. It's kind of trying to force you to use it in a functional way, like Haskell or similar programs. But it's not something you can't avoid. You can choose for yourself. So you create a structure type, then you can create a structure. Once again, you create the data, you assign it, you bind it to some name. In this case, ABC is going to be 1, 2, 3. If you want to access the structure field, it's very different to traditional languages. There are defined accessors which are named by using a combination of the structure name, dash, and the field name. This way we can access the ABC in our myData basically variable. And if you want to modify something, there's another useful thing that's the not the accessor but the modifier, and it's always set dash the structure name dash the field name and exclamation mark. Usually in Lisp-like languages we are using exclamation marks for something that modifies something that's been created previously. Because you have to be careful with that, especially if you're writing large programs which use some parallel computing and stuff like that. You can easily modify something under your hands and you don't want to get some unexpected results. So these are simple structures. Of course, there are also classes. We'll get later to why I'm talking about them. It's basically like structures, just with different syntax, and you can add methods. So if you want to create a new class, you just say, once again, you create the class, and again, the type itself is a value, so I need to bind this value to the name. And this is a simple class. There's a definition of a superclass. There's a definition of some fields that get initialized no matter what you do. Then you call the superclass's initialization, and then we define some public method. Everything at once. I tried to squeeze this on the slide, and somehow this is a code that actually works if you write something meaningful instead of those ellipses. The classes in Racket form a tree with just one root, and that's the object class with the percentage mark. And actually that's a naming convention. Usually classes end with a character, the percent mark. It's not necessary. You can choose for yourself, but it's a naming convention everybody's used to, so if you are in trouble and you're asking someone for help, it helps with the readability of code. Of course, you can have something you probably know from Java and other languages, interfaces. It basically is a definition of what kind of methods the class should implement, or in this case, must implement. It's rather simple. You just say, this is my interface, and it can have some super interfaces, so it inherits the definition from those super interfaces. That's the list. In brackets, the interfaces ellipsis, and then you just write the names of the methods you wanted to implement, and that's all. Once again, as I said, the list can be empty. There's a naming convention that interface names should end with the less than, percentage mark, and greater than characters. Just a convention. In some projects, we, for example, use some suffix stating that it's an interface. It depends. In this case, you're basically free to choose, and nobody cares. So if you want to create a class which implements some interface, it's rather simple. You just say that you want to implement that interface and use the class star form, not just the class, but with the star you say there's going to be some interfaces, some fields, and you implement the method. That's all. So we define a class. Now we want to do something useful. As in other languages, Pascal, Java, Python, you instantiate the class and you get an object. So if you want to create an object, you just use the new method. That's a global function that takes a class, initializes it, runs its initialization code, and returns the object. And once again, we just bind it to the name, in this case, my object. Of course, as with structures, you can get and set field values. It's rather simple. You use the get field, the object, and the field name. It's, as I mentioned, similar, but different syntax. That's all. You can set the field value, of course, set field with exclamation mark. We are modifying something, so we need to be careful. And you can call a public method. Are there any programmers in, for example, Smalltalk here? Nope. Oh. Anyway, it's still gonna be fun. In Smalltalk, you are not calling methods of an object. You are sending a message to the object, and the object sends you something back. So this is the same thing. You say, send to my object some method name and some arguments, and it will take care of whatever is needed to do and return you the result. So that's basically it. And the main reason I'm talking about this and why I'm talking so quickly, because I needed to cover it, because it's used by Racket Draw and Racket GUI libraries, and that's something we'll be using. So after this short introduction, I'm pretty sure if you never programmed in anything like Scheme or Lisp, you have no idea how to do it. Don't worry. This is going to be just a few showcases where it can help you, and you can easily learn it later. It's got really simple syntax that helps. So, first example, embedded computer vision for manufacturing QA. We're using Racket on a Raspberry Pi with some 3D printed stuff around. We are looking with a camera on a PCB, that's printed circuit board. We've got attached some sensors for temperature, voltages, and whatever. And we are trying to make sure everything works as expected. You know, you get the batch of PCBs from the factory. Some of them work, some of them don't work. So you need to distinguish quickly which are which. So how do we do it? First, what we are running on the Raspberry, of course, Raspbian or Ubuntu. Why? We are lazy. You know, it just works, and in both operating systems, Racket just works. So for the first units, we mostly used Raspbian. My colleague installed Ubuntu on some later units we developed because he needed some other software that was already in Ubuntu and was not in Raspbian. It really doesn't matter. As long as it's some reasonable GNU Linux, you're fine. Good thing is, you can use the latest features of the newest Racket if you use the nightly builds, because they're basically sort of distribution-independent binaries, even for ARM. So if you've got any 64-bit or 32-bit ARM board, it will work. You just unpack an archive, set the paths, and it works. So that's cool. Of course, if you are using Ubuntu on a laptop, as I do, although I do not like Ubuntu that much, but you know, you just plug the USB stick, and in an hour you're working. And because I often destroy my laptops, this is a feature that really made me stuck with Ubuntu. The good thing is, if you use PPA APT source, it's just there, and it keeps you updated with the latest stable version, so that's cool. Now, up until now, I was talking about what Racket can do, but there are things Racket can't do. One thing, if you're using Raspberry Pi, there's a very specific camera circuitry, and you need to use either some specific library or the Raspistill binary. So that's what we are using. Now, but in Racket, we can load any bitmap the Raspistill produces. So, for example, BMP, PNG, JPEG, although you can guess that JPEG is not very useful for this task because it's a lossy compression. And by the way, it's turned out that the best way to acquire images on Raspberry Pi is to just store it in BMP in a RAM disk, because then you can just memory map that and use that. But let's be lazy. If we want to get image from Raspberry Pi camera, the function fits on a single slide. We just get some temporary name. We just run the Raspistill with some arguments. Actually, it's a rather long list because, you know, we are using it to capture image of lit LEDs. So we are using something like 700 nanoseconds shutter time or something like really short. So that's the reason I'm not providing those, because it's rather long and it doesn't matter. Choose whatever you want to use with Raspberry still. And then we just create a new object. Make object is just a different name form for new. If you don't want to put the names there, if you just want to provide the arguments there, because as I mentioned, let's be lazy. And then you delete the temporary file and return that object. So although Racket doesn't have a functionality to use any camera, on Raspberry Pi it was rather simple to implement. So after we've overcome this limitation, how do we work with that? Turns out Racket's bitmap class cannot read what's inside the bitmap. Might sound strange. Why the hell is he talking about this if it can't even read what's in the bitmap? Well, nobody wanted to use it, so nobody implemented it. But we wanted to use it, so we implemented it. Although there's no way to read pixels, it's rather easy to get the alpha channel, red channel, green channel, and blue channel for all pixels as a one huge bytes array. So we can use this method to get this array, actually a vector of bytes, and we can implement a pixel reader. And this nicely shows all the features of Racket, why it really helps with some rapid development. You want to read pixels from a bitmap, so you check what's its width and height, you load the bytes representing all the 4 channels into a byte array, and then you return a new function. And this function accepts coordinates, and based on these coordinates, it reads the data from the bytes array. So basically, we are here defining something that creates a new function for each and every image we provide to it. And actually, this is how you solve problems like this in languages using some higher order calls. And the funny thing is, behind the scenes, it actually provides pretty efficient implementation. Although it looks slightly cryptic, it's rather fast, which is why we are using it. Now, Colorspace conversions. You might ask, why didn't you use, for example, OpenCV? We did a year ago, and we spent 3 months on that, and turned out that it's not stable, it leaks memory, and it doesn't work, at least stable versions, as we needed them to work. So we implemented something on our own. We needed to do some fuzzy color matching in hue saturation value color space. So we did a simple converter from RGB to HSV, and it shows another nice features of Racket. You can define multiple values at once. You can use any symbolic expression in place of anything in the code. So basically, you can write a very short code, which is pretty readable. I know it doesn't look like it's very readable, but think about it as a mathematical expression. If you think about it as a mathematical expression, it looks like any other formula or equation. So basically, it maps one to one. You might be, once again, confused by the prefix notation, you know, the slash and plus and everything is at the very beginning. But think about it. If you are writing, for example, sine or square root or other functions, you are writing them in front of the values you are trying to square or get a sign for. So it just generalizes this idea that even normal arithmetic operators are just functions, and you call them with prefix notation. And in this case, we return a list, which is another function which takes some arguments and returns a list which contains these arguments. That's, you know, the LISP-like list from that lots of irritating, stupid parentheses abbreviation. Now, after we did all of this, finally we got to be doing something interesting. We needed to find spotlights, because as I mentioned, we've got some shining LEDs there. You want to find them, we want to check whether they are shining when we want them to be lit, and whether they are dark when they should be dark. So for finding spotlights, we did some thresholding of the pixels based on their HSV part called value, that means on the intensity of the light. And then basically we scanned the whole bitmap and we were averaging the positions of each and every pixel, and we used the weight of the, as a weight we used the value of the pixel, that means the intensity. Then again, once we found the spotlight, we needed to check the color. Now you say, okay, but how do you check the color? Either you can do it as a computer, so all the values RGB or HSV are equal to what we want, or you do it as a human. You see it's sort of red, it's sort of green, it's sort of orange, and the bad thing is we needed the latter. We needed to check it like a human, not like a computer. So we implemented a blurred color picker, which takes a few values, actually quite a lot of them, around 300 or 400, and creates a weighted average of those for a given area. And the weighted average is that the weight of the pixels decreases based on the distance from the center. Actually, it's rather simple. We are using this formula, and you can imagine the weight of the pixels as the cone depicted on the right. So that's rather simple. And once again, why Racket? Because when you are using formulas like this, you really translate them to Racket directly. You don't need to write some complex functions and debug it. No, you just write the mathematical formula and it's there. And for matching colors, you know, because we don't have much time, I can only say it's trivial. And so it's rather simple, just comparing some ranges. Now for the nice pictures. This is what it can actually do. So after, and this was like 2 days of implementation, so really it was quick. After those 2 days, we were able to take the picture from the camera and check what color each LED is and match it to some classes. Like we are using, as you can see, red LEDs, we're using some orange, green, some whites. The whites are really bad thing because they are not white. They are slightly bluish, so that was another thing we had to solve. But it went pretty good, and we're using it ever since. Now, the thing is, as I mentioned, we are using 3D printed components on the testing jig. So nothing is very precise. And therefore, when you want to match the LEDs, there can't be fixed positions of them, like on the picture. So the first thing, actually, after we get the picture and we find where the LEDs are, we use a simple affine transform to transform it from the space of the picture to the space of the design of the PCB. And we're actually loading the data files of the PCB specification, and there are coordinates of various components of those LEDs, and we just match it and transform it. So no matter how you put it on the test bed, it will find it and sort of tilt it or rotate it or whatever is needed. So let's get back to some simple algebra. You've got some point in the original coordinates, you've got some point in transform coordinates. You can compute some transformation matrix, which you can apply by multiplying the point in the picture by that matrix. You get the transformed picture, pixel, yeah, actually point in this case. And once again, that's trivial in Racket, and you might have guessed it because of all the operations you've already seen. And the thing is, not only it's trivial, but once again, you can use the ability to create new functions in runtime to do this, because you can create a function that you feed the positions in the picture, you tell it the positions in the scheme, and it will do all the computation and return you a function which you just apply to points in the picture, and it transforms them for you. You don't need to do any math in the code which is doing something else. So that's pretty neat, and this is one of the reasons we are not using, for example, Python, because in Python the lambdas are implemented just like a quick hack and not the real thing. How does it work? Another nice picture. if you look at the top left, you can see a magenta cross at this slide, another one here, and these are the points where it fixes the transformation. Then it calculates the transformation, and you can see it nicely marks all the LEDs in the image. So that's why we needed to do it like this. Now let me venture into another feature of Racket. It's called parameters. You know, the global variables are the root of all evil, or at least some theorists say that. They can at least give you a headache. Trust me, I know that. But we've got parameters which are like global variables, but they are bound to given context, like a thread or some part in your execution stack tree. Why is this different? Well, if you modify a parameter and you are running some code, you can be sure you modified it. If someone else in the meantime modifies the same parameter, that's not a problem. There's different context, it doesn't affect you at all. So if you want to create a parameter, yes, you say make parameter. In this case, I'm giving it a false value as a default value. If you want to use it, you can just call it like a function. It behaves the same way. And if you want to change it, you can use parameterize form, which changes the value of the parameter just for your context. And in the thunk part, you just write the code. It's whatever you want to do there, you do it there. You probably do not see any connection, but wait 2 slides and you're gonna get it. Another thing, of course, Racket has things like vectors, list, associative maps, or associative arrays like Hashmaps. It's the same thing as in most programming like widgets. You can create it by saying make hash. You can add or modify elements. Once again, the hash set function is with exclamation mark because we are modifying something. And of course, there's the hash you want to modify, a key and the value. I'm using quoted symbol here, so the lookup of the key would be pretty fast. It doesn't have to do any matching of the data. Everything on 64-bit platforms is just comparing 64-bit values under the hood. And if you want to get something, of course, you just use the hash ref for reference. Surprise, surprise. Now, why all of this? Because after we do the testing, we need to create some report and upload it to some server and process it and whatever, check the stocks and see what has to be sent back to the factory or what can go on to further manufacturing. Of course, we use JSON. Everyone uses JSON. If you are working with any web developers, you just give them JSON and they do whatever they can and whatever you need. So once again, we were lazy and we use JSON. Generating JSON is rather simple. Many S expressions in Racket can be labeled as JSON expressions, JS expressions, for short, JSEXs. And there's a JSON library installed with default Racket installation. So you just say require JSON, and you can immediately start using it for serializing and deserializing the data you have in anything that can be JS expression. So we use any JSON compatible expression like a hash map. And with the help of parameters, we just output it wherever we want. For example, in this case, to an output file. So there's a variable called output.json. In that variable is going to be some file, a file name. If it exists, it's going to get replaced. And once again, what we do, we provide some lambda function which accepts just one parameter, and that's the output, basically handle of the stream. And using parameterize, we just use the same display line, but now it's going to go inside the file. Of course, for single display line, this doesn't make any sense. But imagine you're writing rather complex code, you are producing some textual data, and you want to debug it. You just display it on your terminal. And then you just wrap it in one parameterize, and within one, for example, call it output file or some network connection. It's up to you. And it's done. It does all the work for you. So that's basically my first topic. This is why we are so happy using Racket, because really we tried something in Python, in C++, we can do it, but it just takes so long, and because we didn't know what we need, it really helped us try many dead-end paths and finally come up with something that works pretty quickly. And we weren't too bothered that we have to throw away the code, because, you know, if you have to throw away 2 days worth of code or 2 months worth of code, it's kind of different. Now, second topic, desktop applications. As I mentioned, you can do GUI in Racket. It's cross-platform. You can use it on GNU Linux. You can use it on macOS, even on Windows. And another thing, we are using a foreign function interface. For most of the libraries you are used to in C or C++, you don't need to write extensions in Racket. You can just sort of tap into them and use them with a foreign function interface. And the funny thing is, it really works cross-platform, so you can use the same way of accessing some shared library functions on Linux, like the shared object file.so, and on Windows.dll, dynamically loadable library, which is pretty cool. Let's have a look at GUI in Racket. Another nice pictures. First thing, of course, top-level window. It's called a frame. Who knows why? Probably for historic reasons, but it works. You can create it by instantiating the frame class. You set some name to it, for example, some initial dimensions if you want, and then you just send it the message, hey, show, and the value true that you really want to show it, and false for hiding it. And it sort of displays a window. The program ends when you close it. Pretty cool. What else? We want some action. That means we want to click on something and it should do something. So we can create a clickable button with an instantiation of a button class. Of course, you have to provide some parent where to put the button in GUI. I think everyone who is doing some GUI knows about the containers and stuff like that, so I'm assuming you sort of know what I'm talking about. And you can later on, or in the instantiation, specify some callback. It's not here because it wouldn't fit, but it's called callback. So it's rather simple, and you just provide a function you need to call. Then some informative label. It's called a message, just a text in your GUI, typically a label called in other toolkits. Once again, just instantiate the message and is there. You can see the examples. A button, yes, it looks like a button. A message, yes, it looks like text. Really easy. Now, for layout control, you can stack things vertically, putting them into vertical pane. You can stack things horizontally, putting them in a horizontal pane. It's rather complex if you want to combine them, so just a simple example here. You can provide some borders. And here's a simple GUI, which we're actually using for flashing a new firmware to our devices. And this is on Ubuntu. It looks the same on Windows, and it does what you would expect it to do. So you can load some file there, you can flash it to the device, and you can quit the application. Really rather simple with just vertical and horizontal stacking of widgets. For foreign function interface, mostly two libraries are needed, and that's the FFI unsafe and FFI unsafe define. That's because you know, the unsafe words should say it all. They are unsafe by nature. You can directly access program resources like memory, so you can crash things. Like really, you can crash the Racket runtime. But you can do a lot of useful things. You can access binary structures like those in C libraries. You can call a C library function. You can manage memory buffers manually. You don't need to rely on a garbage collector. You can say basically memory allocate, memory release, and it works. Or you can allocate memory and let the garbage collector take care for the release of resources. It's pretty cool. And you can even call back from your C functions to the Racket code without programming any C. It's also pretty cool. So if you want to load a dynamic library, you just say FFI_lib and the name of the library. And then you can provide a fail keyword-based argument, which calls some function in case it fails. So here you can see how we load HID API library on Linux and Windows. And it really works because the first call fails on Windows, but the second one succeeds. So we got a handle for the HID API library on both systems. Now, of course, if there's no fail and it fails, it raises an exception. Now, if you want to use some structures in the code, you must define a C-style structure. There's a define C struct for that. That's why we required that FFI unsafe define. You just say how you want to name things and what type it should be. There are underscores everywhere. That's to let you know that you are working with C code, and there are underscores everywhere. This is for some HID device information, just the beginning. Now, if you want to call some functions, you first need to define a definer for the given library. Definer means, hey, here's a library, and I want to use some functions. How do I do that? With a definer, which is basically a function that can give you access to functions in the library. You just bind a function to some symbol. So in this case, I'm using the newly defined definer to bind the HID enumerate function to the same name here. There are some naming conventions. There are some call conventions, like it's a function. It expects you to give it two 16-bit numbers, and it returns some structure, some pointer to a structure or null. So that's also defined in the FFI unsafe definer. And with this, that's all you need. With the enumerate we are using, we've got a GUI application both on Linux and Windows, and detects if you insert the device into USB port, and it can work with that. Cross-platform, no further work needed, which is really cool because I don't like developing on Windows, so I'm working on Linux only, and then we just compile it on some VM to produce. Actually, in this case, no, that's not true. I'm using Wine with Racket installation for Windows under Wine, and that produces Windows binaries directly. It's pretty cool. I don't even have to run Windows now. So we've got like 5 minutes left, and now it's the most interesting part for all of you mathematicians. Wow, I was sort of expecting, wow, that's the thing. Okay, no, never mind. So, big numbers crunching. In June this year, I was tasked with developing some number crunching software for a company that needs to optimize their invoices they give to a bank, so they can get some money from the bank. Pretty boring stuff, but interesting mathematically. They wanted to do it on their own, and they got stuck because they realized they've got like so many combinations with just a few invoices. In the case of 27 invoices, it was 2 raised to the power of 27, so it's 134 million combinations, and they had no idea how to work with that. So what I did, and actually I got paid for that, so you get paid for writing in Racket, I tried to do this as fast as possible. So if I ask you, hey, here's 100 million numbers or 1 billion numbers, how do you sort them? You say, oh, that's pretty easy. Then you try to write it, and you realize it's not that easy because, you know, 134 million numbers, 64-bit numbers, 8 bytes each, means 2 gigabytes of RAM. If I add another thing there, it's going to be 2 raised to the power of 28. It's going to be twice as much. And honestly, 2 raised to the power of 32, and you need something with at least 256 gigabytes of RAM. Not a good start, but let's try it. First, with the lists. So what I did, to test the idea, I created a list of 2 raised to the power of 27 numbers. Rather simple. Exponent, you can use the simple for form, which creates a list with whatever you provided. And actually, this is not a function that's implemented by the Racket runtime. It's just a syntactic form someone wrote for Racket. It's rather cool. And then you sort it, of course, using the sort function. That's not worth a talk, is it? But there's a problem. It's not very optimal. It required 6 gigabytes of RAM, and it took like almost 80 seconds to sort. And just to generate the stuff, it took like 30 seconds. All right, I said, I can do better. So there's the one thing. In Racket, you can actually use what's called a Fixnum. And on 64-bit platforms, it's actually 63-bit signed integer, which turns out is quite a lot for us. So then again, it's stored in 64 bits, which means 8 bytes. So we are not sparing that much. But the thing is, arithmetic operations are much faster with Fixnums because they are platform dependent, and it's not that you need to check the type before you do the operation. Of course, you can't use a simple plus or minus. You have to use fx plus or fx minus, and the same applies for comparison. You might recall you heard somewhere there's a thing called a Numeric Tower. In Scheme, it's actually a Numeric Tower. You've got a 0, you've got the integers, you've got the rationals around that, you've got the complex numbers, which can be either real or rational, and all this stuff is there. If you omit this stuff and use just the Fixnums, which means integers, 63 bits long, things get faster. So what I did, I implemented a simple merge sort and used another cool thing. I used another unsafe operation. You can even say, this value is a Fixnum. Don't talk about it. Don't ask. Just do your job. Of course, if you provided a string or an object, it will give you wrong results. It won't crash the program because everything is 64 bits long, so it will just provide some meaningless values. But if you know what you are doing, it means all those operations get mapped to CPU instructions directly. So now we are writing really higher level language code mapped directly to CPU instructions. It should be pretty fast. Of course, the operations are named unsafe-fx something. The thing is, the merge sort is used also in the default implementation, and it's not faster. It's slightly faster, about 1 second on the worst case. But you might notice that now we are using just 2 gigabytes of RAM. So there's some improvement. Can we do better? Turns out we can. We can do if we leverage futures. What a future is. The thing is, threads in Racket are almost thread safe. They are mostly never run in parallel. Mostly. We'll get to that. So doing some explicit parallel execution is not simple because the language is trying to force you to do just the safe stuff. But sometimes, if you want to use all the cores and hyperthreads you've got. So you can have what we call a future. It's an expression for which we know we will want the result later on. It's not like a lazy evaluation. It's quite the opposite. You are saying, I'm not needing this now, but in a few moments, I will need it. So how we define that with the future keyword, it's rather, or the method actually, it's rather simple. And if we touch the future, that's how it's called, we get its value. And the thing is, Racket will try its best to have the value ready before it gets touched. So what I did, I rewrite the merge sort for using futures to achieve actual parallel execution. And actually, Racket gives you an information about the number of hardware threads and everything. So on a 4-core machine, actually this i7 with 2 hyperthreads per core, we get to something like this. Still 2 gigabytes of RAM, but we get down to something like 14 seconds. So it really is 8 times faster. And all we did, we just said these parts of the code should be executed as soon as possible. And the system just took care of that. Now, that sounds simple. It's not. Especially if you are trying to design this, it gives you a headache. But Racket comes to the rescue. There's a thing called a future visualizer. You just require a future visualizer. And the part of the code you are trying to run with futures, you wrap in visualize futures form. And if you do this, it gives you detailed information about what gets executed where. if there are some blocking events, like, for example, if you are doing some input and output, you just can't cross that because two threads can't do the same thing. But if you're just crunching some numbers, it can run in parallel, and it runs in parallel. If you would have, for example, 64 cores, it would really scale to them without any problems. And then, if you want to make sure you designed the way it should get parallel, good. You just look at the features creation tree, and you see what I did in this case. At the very bottom layer, you've got just 8 threads because 8 features are used. The algorithm knows that it doesn't make sense to try to use more features because they will not run in parallel. You get just 8 virtual cores, 8 hyperthreads. So with this, it's rather easy to make sure you're using it as you should use it, and it provides the results you really need. And that's all for today. Just a few references. You should look at the typing attempts written by Matthew Flatt and Matthias Fleisen and others. The Numeric Tower is something that's still a part of an ongoing research, how to tie this to a strongly typed system and stuff like that. It's really interesting if you are into programming language theory. And of course, look at racketlang.org. It's really simple, and I'm pretty sure you will like it. Any questions? I knew it. Oh, if I'm using this, if I'm running it with Racket command or GCC. Actually, how do we produce binaries? That's a good question. Racket itself, if you use it just as Racket in the program name, it compiles it every time, which is not very efficient. But there's a tool called Racket, which does useful stuff there, and if you call it Racket.exe, it produces the compile bytecode and prepends the runtime to it, so it produces the binary for the platform you're targeting, like Linux in this case, or Windows. No, I don't think so. Actually, that's something I'm missing there, but I don't have time to implement that. That would be cool. Good, at least one question. I'm happy. One more. Now, that's a good thing. You know, a friend of mine, like 20 years ago, was really into Common Lisp, and it just didn't fit. And in 2003, I started working on various projects in Scheme, mostly Guile or some variants used in audio processing, because, you know, the nails, I'm a musician, so I'm doing a lot of recording stuff and audio processing. But the problem is, nothing really worked as I wanted to work. And like 6 years ago, I just encountered Racket, and hey, this is the scheme I always wanted. So that's the thing. It just works. Cool. Okay, so thank you. Thank you for coming. At least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of you. And of course, here AVC lady, thank you as well. And now you know why you should become a Racketeer. That's how we call ourselves.